All right, so for part C, it's asking you to determine f bubble g of x, that's composition. It really means f of g of x.
Okay.
And so what this means is to take the inner function, 3x, and replace it for x in the other one.
Okay.
So it's like wherever you see an x, you replace it with the other function.
Okay.
And that's it. There's no more work to do. Like it feels like, oh, well, isn't there something to do? It's like, nope, there's no numbers. It's just figuring out the composition of the functions.
Okay.
We actually do this all the time in real life. It's just math kind of makes it a little weird. We take the output from one thing and it becomes the input to another.
Yeah.
But this one is going the other way. It's saying, take f of x. You always start with the inside one and put it in for x in the other function.
Okay.
So this becomes 3 square root of x plus 1.
Okay. Got it.
Any questions on that?
No.
Okay, so number 2, I was looking for this, but I guess I didn't look far enough ahead. So we first need to go back to f of g. Grab the functions here. All right, so we first actually should look at the domain of each of these. And the one on the right for the 3x, it's a line. It's just a straight line, goes up. Its domain is all real numbers, or minus infinity to infinity.
Okay.
But square root of x plus 1, well, its domain is not. Do you remember what you cannot take the square root of?
Isn't it -1?
Negatives, right? You cannot take the square root of negatives. So the domain for square root of x plus 1, you take the part under the root and set it greater than or equal to 0.
Okay.
So to solve this, you subtract 1 from both sides, and x is greater than or equal to -1. And that's the domain. It's -1 to infinity. Now, this is just kind of the start of this. This is not everything, but it's the start here. So you typically find the domain of the original functions, then we can do this domain of the composition stuff.
Okay.
All right, so the first one, the f bubble g, it became, if you look back, it became, sorry, I'm just looking back here. It became the square root of 3x plus 1. Okay. And so what you first do is you actually look at the inner function g of x. And did g of x have any restrictions?
No.
No. But this new one does. So you first look at the original function, then you look at the composition. And you decide, well, does this have any restrictions? And again, it does. 3x plus 1 has to be greater than or equal to 0. So solve this, subtract 1 from both sides. 3x is greater than or equal to -1. Divide by 3. X is greater than or equal to -1/3.
Yeah.
So that's your domain. Your domain is that it's all real numbers from -1/3 to infinity. All right.
Okay.
So now we got to do the other direction. We got to find g of f of x. We did this earlier. It ended up being 3 square root of x plus 1. So you first start with f of x. And you're like, what was the domain of f of x? The f of x is the original function. Its domain was -1 to infinity. And you look to see, like, well, does it change? Like, does this thing have a different domain than this one? And they're actually the same, because it's basically the same function with just a 3 on the outside. So that's -1 to infinity is the domain.
Okay, got it.
All right. So this domain business looks like you're going to be doing a lot of here.
Yeah.
I know it's probably confusing. So yeah, these are not the best examples to be learning it for the first time. It's better if you've had a little more kind of build up to this, but
Yeah, well, we
that's what
did,
we
but
got.
it's just like, I forget it.
Yeah, and this is hard for most students. This whole like idea of domain, its restrictions, it's
Yeah.
not easy. It's not like other stuff you've been doing, which I think is a little more intuitive. So kind of the
Mhm.
same thing here. We need to find the domain of each of these.
Okay.
Okay, so the other thing you can't do is you can't divide by 0. So if you look at the first function, what value of x makes the bottom equal to 0?
-4.
So for g, for sure. So for this other one here,
Oh, yeah.
we need to do them both, so that's good. So 2x equal to 0. So what we're saying is, I think that's kind of where you're going, is on the one on the right here for g of x, its domain is everything but -4.
Yeah.
So it's all real numbers except for -4.
Okay.
The other one is restricted at 0.
Okay.
All right. So now find f of g of x. I'm sorry, g of f of x. And then the domain specifically, you first figure out like what is g of f of x. Like you have to actually do this, which means to take this and plug it in wherever you see an x. And that's where this gets really, really dicey. I mean, it's got so much going on here. It's
Yeah.
8 over 5 over 2x plus 4.
Oh, wow. Okay.
Yeah, and it looks bad. It is bad. It's not nice. We have to simplify this to do that, you make a common denominator on the bottom here. So if we're just looking at the bottom, common denominator will be 2x. So for the one on the right here, you multiply the top and bottom by 2x.
Mhm.
So this becomes 5 plus 8x. Keep the 8 there. And then on the bottom, because the bottoms are the same, you can combine the tops like that.
Okay.
Do you remember what to do here?
You can take 2x out of the bottom.
And move it to the top. Something. So it ends up being like you're multiplying by the reciprocal. I'm going to show that here. You're multiplying the top and bottom by the reciprocal.
Okay.
And so the 8 is really 8 over 1. And that's why the 2x ends up going to the top. It ends up being 16x over 5 plus 8x.
Okay.
Okay, so you might be getting me wondering, why are we even doing all this? You have to look at this new function and also find its domain.
Okay.
So you'd have to set the bottom equal to 0, 5 plus 8x equal to 0.
Mhm.
Can you solve that for us, please?
Yeah. Is it -5/8?
So x cannot be -5 over 8.
Yeah.
Okay, so that's the domain of this thing. And what you have to do is you actually have to compare it to what you started with, which is f of x. You always start with the inside function. So the original function was only a problem at 0. 0 was bad, but everything else was good. The composition is bad at -5 over 8.
Okay.
So they are both bad. There's problems at two places, -5/8 and at 0.
Yeah.
Because it's almost like you're combining these into a new number line where you say, okay, it's bad at -5/8 and it's bad at 0, but everything else is okay
Okay.
from -infinity to infinity. So you guys, I assume you're using interval notation. I can't say I know for sure.
Yeah.
But okay, so it's -infinity to -5/8. Union -5/8 to 0. Union 0 to infinity.
Okay. Got it.
Got it. Okay. All right. So next set of questions here, next kind of grouping, kind of moving to inverses of each other. Are the following inverses of each other? There's a couple of ways to do this. One is to actually determine the inverse, and then the other is to use composition. Do you know which way you guys were doing in class?
I don't really.
Okay, so method number one would be to actually determine the inverse of, say, this one, and then do the same thing for this one. And then if you find the inverse and they are actually the other function, that's good.
Yeah.
The other way is to do the composition. Now, based on what I've seen, I guess you probably are doing composition. So we probably should do that.
Okay.
So we first need to do f of g of x and then g of f of x. So f of g of x, the one on the left here, you're taking this right here and putting it in for it. Will you attempt to do that for us, please, and let me know what you come up with?
Okay. Is it the square root of x squared? I can't hear anything.
Oh, I apologize. I apologize. I was drinking some water.
Oh, you're good. I didn't know if like you were talking or something.
Yeah, you're putting everything in for x, but you're keeping everything else, like -2, the parentheses, the squared, and then you try to simplify this.
Oh yeah.
So what can you do to simplify this?
The 2 minus the 2.
Yes, so this becomes the square root of x squared. What does
Yeah.
that become?
Just x.
X, and that's what we want. If they're inverses, they both become x, but you have to do both compositions. So now you have to go the other direction. You have to take all of this, parentheses x minus 2 squared, and put that in for x like that.
Okay.
So it's the square root of x minus 2 squared plus 2.
Okay.
Will you try simplifying this for us?
Mm-hmm. Is it just x again?
It is just x, yeah. So these are inverses when you get x for both.
Yeah.
And they both have to work. You will see questions on a test where they work only one way, but not the other. You have to be very careful that you don't assume that they work.
Okay.
All right, any other questions on that before we move on to 5? 5's kind of a lot here, but
No.
we'll do it. Okay. All right. Okay, let me snip in a few things. All right, so we are going to calculate the inverse function. We'll work on doing that here. But there is something really important about the domain and the range that's related. So whatever the domain is, it becomes the range of the inverse. And whatever the range is of the original, it becomes the domain of the inverse. Have you seen that before
Yeah, I
in
have.
class? Okay. So for example, when we look at this 3 over x minus 2, we know the domain, it can't be 2. 2 makes it 0. Like it's everything except for 2. It's all numbers, minus infinity to 2, 2 to infinity. That becomes the range. Like you don't have to do any work. And there should be a union there. All right. Now in terms of the range, this is heavier on the bottom.
Uh-huh.
Do you remember what that means for the range or the horizontal asymptote?
Does that mean that y is equal to 0?
Yes. So we don't know exactly what the graph looks like, but it approaches, it never crosses 0 as far as we know. So that means minus infinity to 0, union 0 to infinity. And again, that gives you the domain. Like without really doing any work, we have a lot of the information here that we need. All right. Now to the task of actually finding the inverse. Okay. So you start, it's a recipe. I don't know if you like cooking or baking, but it's really a recipe. There's step 1, there's step 2, step 3, maybe a step 4, depending on how you do it. So step 1 is to replace f of x with y.
Yeah.
Step 2, the numbering the steps isn't all that important. You switch x and y.
Mm-hmm.
And then from here, you have to solve for y. And this is where I think most students get tripped up. Either they don't have good algebra skills or they're just not sure how to proceed. You might think of x as being x over 1.
Mm-hmm.
How might you solve this? Any idea for y? How to get y out of the bottom?
Do you do something to the 3?
Usually cross multiplying is the most common way. You could flip
Okay.
fractions, but I would recommend just cross multiplying here. Now you treat the bottom right like it's in parentheses. So it's x times y minus 2 equals 1 times 3. Right, and because we're solving for y, you really want to get rid of this x here. So you end up dividing both sides by x.
Okay.
Y minus 2 equals 3 over x. All right, we're almost there. What do we do to solve for y here?
+2.
Plus 2. So y equals 3 over x plus 2. And then maybe a final step here is to write f inverse instead of y, but this is it.
Okay.
So if you go back to this right here, 3 over x plus 2. You really do have to work it out the way we just did. There's no way to kind of pattern it, even though it kind of looks like, well, it's got a 3 there and a 2 and a 2. Like, no, that doesn't work. Don't try to make that thing there.
Okay.
All right. So next thing is to graph it. Are you supposed to graph these by hand or
Yeah.
no calculator, no Desmos? It's just so much easier.
I don't know. I don't think he said so.
All right. So the reason there's a table here is that your table flipped gives you your inverse. So I'll show you that in a moment here, but let's put some values into this table. Let's see here. 1 is a good value to use. 3 is a good value to use, and -1 is a good value to use.
Okay.
Okay, so can you give me the y values in each case here?
Mm-hmm. Hold on. Three is -1.
Say that one more time. Which one are you doing?
Oh, -1 is -1, right?
Yes, that looks right.
And then 1 is 3.
1 is -3. -3 because 1 minus 2 becomes -1.
Oh, yeah. And then 3 is 1.
Okay, so this really isn't enough to graph this, but I mean, I don't know how much. Like this take. I mean, you could do a whole lesson on graphing rationals, but we got some points here. There's a vertical asymptote at x equals 2. There. Let's just plot some of these points. So we got -1, -1. I should probably do this in different color. Let me do it in blue. -1, -1. 1 minus 3, and then 3, 1. No, that's in the wrong place. 3, 1 there. So it's probably hard to see, but it looks like this.
Yeah.
And then the thing that they should have been telling you in class is that the line y equals x is what you are, the inverse is what it transforms over. You're going to see a mirror image of this when we graph the other one. The other thing is though, is that these ordered pairs here, you flip them for the inverse. So what I mean by that is for the inverse graph, and I'll do that in green here. You just flip the x's and the y's.
Okay.
And that gives you some points to graph on the other one. So you do get one that's exactly the same. You get that one there and that one there, but there's actually a bit more to graphing this. So, I mean, this is not a full on graph.
Yeah.
So I don't know what to suggest here. It's actually kind of difficult to do. The 3 over x plus 2 has a horizontal asymptote at 0.
Okay.
I'm sorry. That's wrong. I apologize. Yeah, I'm sorry. Vertical asymptote at 0. Maybe I said the right thing. And then it's got a horizontal asymptote at 2, which if the y equals 2 there. So graphically, it looks like this. And then the other one looks like this. And you're supposed to sort of see a mirror over that red line, which I think you can kind of see down here, but the other one's a lot harder to see.
Okay.
So if you enjoyed that, I think we got another on this. Unbelievable. Okay. Any questions on that before we proceed?
Hold on, I still have to copy down the rest of the
Okay.
graph. Okay, I'm good.
Right. So the next one here, part B, x squared plus 4, x greater than or equal to 0. domain and range. So I just need to make a few snips to get this kind of figured out here. All right. Okay, they're telling you the domain right here in the top. And we'll get to why that is in a moment. The domain is 0 to infinity, and that tells you the range of the other one. You just immediately write that down there.
Okay. Got it.
All right. So now the range, this is where we got to go and graph this. And you probably haven't done this in a while, but I'm going to show you this in Desmos. I know you got to do it by hand, but this will go a little faster if we can do it this way. Let me clear out what I had graphed for the other student here. All right, let me go ahead and share this screen. All right, here we go. So if I graph y equals x squared plus 4, this is a parabola. You've seen this a bunch. Okay. Now, if I graph a line like y equals 10, if I do it correctly, how many times does this horizontal line hit the graph?
Twice.
Twice. So this does not pass what's called the horizontal line test.
Yeah.
And that's why the domain is restricted. And we can do that in curly braces here. If we write x greater than or equal to 0, you can see that now only part of the parabola is graphed. Okay. And this also helps with the domain. I'm sorry, the range. We can tell the range from this picture here.
Yeah.
So sometimes, I know you can't use this, but sometimes it's good to just go use the right tool and see what, it's kind of like using training aid in sports. You just go see what it's supposed to look like, and then you go back and work on it. Let's go back to our workspace here and quickly do a graph of what I just showed you there, because you kind of need the graph for the range. Like you can't really do it otherwise. So if you noticed when you graph x squared plus 4, if you do like 0, you get 0, 1, you get 5, and 2, we kind of run out of values there. So
Okay, wait, what was the range again?
We're going to do that. We got to graph this first. So that's right. This is 0, 4. So the graph looks like the 0, 4, 1, 5. Anyway, so it kind of goes up like that. This is the smallest y value here at 4. So that's the range. The range starts at 4 and it goes up forever. It goes 4 to infinity.
Okay.
So what is the domain of the inverse?
The same thing.
The same thing, yeah. Okay. Now to find the inverse, we have to use that recipe again. But we can also, as we started the graph here, let me finish the inverse stuff on it. So if you flip the ordered pairs, you get the inverse. So it's 4, 0, 5, 1, 2, 8. So you end up getting something that looks like this. And you can again see that it's mirrored over this line y equals x.
Yeah.
All right, and we can actually figure out the function here. So let's go y equals x squared plus 4. Switch x and y. What would you do to solve for y here?
I would subtract 4 on the other side.
Subtract 4 and then take a square root.
Good.
So it ends up being y equals x minus 4 square root.
Got it.
All right, great. So 37 minutes later, we got done with one page. I feel like we're moving pretty fast. I mean, I don't know if um, you felt that way, but it
Yeah.
sometimes it's like, oh, it's only, whatever many problems, and it's really a lot. Okay, so let's look at number 6 here. It does refer back to what we were just doing. It says, why does the function, and we kind of already answered this, why does the function f of x equals x squared plus 4 from number 4b have a restricted domain? We talked about that the graph of this does not pass the vertical line test.
Yeah.
So I think that's what they're looking for. You'd say the horizontal line test. A horizontal line hits twice. Okay, and that what that means is that it's what's called not 1 to 1, and that's very mathy, but it's what kind of the full answer
Okay.
is here. Okay. 7. We'll talk about 7 next. All right, so is the function 1 to 1? So a quick graph of this would be good to do. It doesn't have to be very accurate, just has to be some sort of a graph. So -1, 4, 4, 2, and then 2 minus 4. And so what you're looking for here is, does a horizontal line hit more than once?
Yeah.
So none of these horizontal lines hit it more than once. Like, you only hit that one point. So it's almost like I need to give you one that's not 1 to 1 to see. So like, let's say I added a point like 1, 4. See how that horizontal line hits it twice?
Yeah.
It's no longer 1 to 1.
Okay.
So it's 1 to 1 if a horizontal line only hits it one time. All right, so 8 is pure calculator. Do you want to skip those? Do you have questions about how to enter in the calculator if you do want to do it?
I can do those later.
Okay, good choice. All right, can change the expression part A. Gosh. Oh, okay. Oh, sorry. It's referring to the ones below it. I see. Okay. All right. All right. So number 9, it says to convert the exponential expression to an equivalent logarithmic function. I think it should say expression there. So I have to sort of give you the answer, and then from the answer you can say, oh, that's how you do it. So this is log base 7 of 49 equals 2. So it's like the 49 goes there, the 7 comes around there, and the 2 goes there.
Okay.
Now the thing that's going to be helpful here is you actually can go backwards. Like, if I give you a logarithmic expression, you can go backwards to the exponential one by doing exactly what I did in reverse here. And so what I'm going to do is snip in part B. And I know it's not written. This has a base 10 here. That's like the 7. Could you attempt to write what goes up here, basically mapping the numbers backwards.
Yeah. Is it 1000 equals 10 to the exponent of 2?
10 to the third.
Oh, to the third. Sorry, I just
Yes. Yeah.
read that wrong.
Yeah. Going back and forth. It's hard here. So there's always a problem like this on a test or quiz. You have to know how to go back and forth. They like give you one or the other, and you end up having to either put it on a formula sheet or writing down an example. But it's not impossible. It's just tough.
Yeah.
All right. All right, so the next set of questions here, it says find the exact value of the following logarithmic expressions. So some of these you could do in a calculator, but these are meant to be done by hand. Like you can see there's no asterisk there. Like the instructor, sometimes they give you like a calculator and a no calculator section on these tests, or they make you show your work. So the first logarithm property that you might need to know here is that if you have log some base of something to the power of n becomes n times log roots b of x. So that exponent basically comes out in front. So in this problem, the exponent of -3 comes out in front. All right, we're not quite done. The next thing here is that log base b of b equals 1. You almost need an example here of this. It's like log base 3 of 3 equals 1. When the base is the same thing that you're taking the log of, it's always that value.
Okay.
So this part is 1, and then it's -3 times 1, so it's -3 total.
Oh, okay, because don't the 5 cancels out?
Yeah, the log base 5 of 5 goes away, and it just becomes -3.
Okay, got it.
All right. So letter B here, we got to do another one. Right. So the next property is log base b of a minus log base b of big B equals log base b of a divided by b. And this is sometimes referred to as a difference, referring to that right there, a quotient. So notice that what happens is you write one log, but the first one goes in the numerator and the second one goes in the denominator.
Okay.
So this becomes log base 2 of 48 over 3.
Okay, got it.
And you divide 48 by 3.
$16.
All right, good. So now this is this feels like, okay, well, maybe this is done, right? It's kind of like factoring. It's like, how do you know when you're done? Well, you do enough of them and you get enough experience to say, okay, like maybe I can do something else. Can you write 16 as 2 to some power?
To the 4th power.
Yes. So this is really log base 2 of 2 to the 4th.
So then it's 4.
Yes, and then what did we do with the 4 or the exponent in the first problem that we did?
We put it in front.
Yes, so it becomes 4 times log base 2 of 2.
Which is just 4, right?
Just 4, yeah. All right, and so let's look at C. C is one of the other logarithmic properties. So you probably saw these in the class. I mean, I don't know how you could go through not see these. They're probably in your
Yeah,
book as
well, I
well.
missed a few days for tennis.
Okay. Yeah, and I was just saying like these are all probably standard problems you guys are seeing. So that's good news. Log base B of A plus log base B of B equals log base B of A times B. And so this is called the sum of the product.
Okay.
So this becomes log base 24 of 6 times 4. So whatever you take the 2 logs, you write 1 log and you multiply what's there. You'll later be doing this with like variable expressions and things like that.
Okay.
And then this is I guess, yeah, we've talked about this. So whenever the base is the same as the thing you're taking the log of, this ends up being just 1.
Okay.
All right, and we'll close out with last one there, D. So this is another property, log any base of 1 equals 0. So it doesn't matter if it's log of 100, of 1, log of
So just 0.
1/2 to 1, it's always 0.
Okay.
All right, and you can find there's like a change of base thing that you can do to get that as well, but this is like worth remembering. So just keep them on all those properties you'll need on like a note card, or you can go out to the internet and find one, but that is it. So just kind of looking ahead here. I mean, I don't know if I couldn't promise you that we're going to get done everything in the next lesson. We'll do our best, but it's pretty slow going here. I'm going to go ahead and stop the recording right here.